Okay, welcome back, everybody. Last time I had finished up with a discussion of Desargues' theorem. This is the main contribution of Desargues to math, and for this reason, he's called the father of projective geometry, because Desargues' theorem is the only other theorem of projective geometry before it was due to Pappus. It's not entirely clear that Pappus actually understood that his hexagon theorem said something about projective geometry, since basically nothing else was done. The kind of sort of the same could be said for Desargues, because Desargues' theorem is basically his main contribution, and not much else was done, although he clearly understood the connection between this thing and projective geometry. So both Desargues and Pappus's theorems are kind of the first two theorems in projective geometry, and as I mentioned before, they actually are the things that give the ability to define multiplication geometrically and allow us to prove both associativity and commutativity of multiplication. This was done by Hilbert in the early 1900s. Okay, so next I wanted to continue the discussion with Descartes. So Descartes is probably one of the more famous mathematicians, or one of the mathematicians that whose name is repeated quite often in your studies, because automatically when you see Descartes, you might think the Cartesian plane, right, which is named after him, and which is his biggest contribution to math. So a little blurb about Descartes. So he was born in 1596, and he died in 1650. So he was born to a noble family. He had sort of fragile health most of his life. So from an early age, he was basically permitted to stay in bed long past hours when it would be reasonable for a person to remain in bed. And so much of his early learning and a lot of his later mathematical work was basically done while laying in bed. He was educated by Jesuits. They allowed him to remain in bed, all throughout the morning. Basically, even when he was in the military later. So he served in a couple of armies during the 30 Years' War. His post allowed him to also mostly remain in bed. Basically, he, even on these campaigns, he would lay around in bed thinking about philosophy and mathematics. So he's already, my kind of guy in terms of laying in bed thinking. That's one of my favorite activities too. So anyway, in 1621, he gave up his posting in the army, and so gave up military posts and traveled for 5 years, I believe. So traveled for approximately 5 years. studying mathematics, uh, before eventually settling in Holland. And he stayed in Holland for about 20 years. So stayed in Holland for approximately 20 years, and this is where he did uh, most of his work that would make him famous later. So in 1649, he went to Sweden to live to be the personal tutor of Queen Christina. So became personal tutor to Queen Christina, who was young at the time. I can't remember her exact age, but she was young, and he was basically her private tutor. Um, and there's actually some pretty hilarious correspondence between them that you can read. So I'll throw up links to those things in the info dumps, or translations of those things anyway, in the info dump. So there's some pretty funny back and forth here. So they had kind of a rocky relationship because she was very opinionated and very strong-headed, and Descartes, he just wanted to kind of lay in bed, right? So um, one of the things is that she insisted on having lessons in math really early in the morning. So she insisted on having her math lessons be at 5 a.m., which totally frazzled Descartes, who was not used to waking up that early. And within a few months of this horrible schedule of having to wake up at 5 a.m. To teach the Queen math, he got sick and died of pneumonia. So that is a lesson. You've spent your whole life, sleeping in, taking it easy. It's not good to upset that too much. So anyway, in this period when he was in Holland is when he did most of the work that you know him for. So in 1637, let me get the full title of this work. So Discourse on the Method. Is all I will say. So that's 1637. So he publishes Discourse. So most people just call it Discourse, but Discourse on the Method has a longer title than that, but this is good enough. So 1637, he publishes Discourse on the Method. This contained a few appendices of interest. So contained 3 appendices. So the first appendix was about optics and the laws of refraction. So Appendix 1 was about optics and refraction. Appendix 2 was about atmospheric phenomena and things like the shape of a rainbow. So atmospheric phenomena. And Appendix 3 is the big one, which was just called geometry. Okay. This appendix is where he lays out his idea for bringing together algebra and geometry. So what was the idea? The idea, of course, is the thing that you're very well acquainted with, that a point in the plane, right? Previously, when we wanted to write a point in the plane, we would label that point P, and then maybe we would have some other figures in our plane, but this was our only way of describing the point, right? But Descartes had the idea of considering a point being described by two parameters, right? An x and a y, where the x is some distance in this direction from a point we call the origin, and y is the distance in this direction from that point we call the origin. So we could label a point like this as an ordered pair, x, y, right? And this changes everything, right? So this has been ingrained in you, for a very long time. So throughout your, I don't know when the first time you saw this, but it was probably very early, right? I think I remember drawing some, I remember doing some graphing exercises when I was like 9, where, there would be some list of points that you would plot in a certain way and connect the dots in this particular way that it would end up being like an elephant or a frog or something once you did the whole picture. But it had you connecting certain points to other points, which was really just an exercise in plotting these things and being, comfortable plotting points in the plane and drawing in lines between points in the plane. So it can be easy to kind of miss how big of a deal this is, but the Greeks had nothing like this. Okay, so the Greeks did not have this way of algebraically describing these geometric things, and this is a huge handicap. This is something that, without this description, it becomes extremely difficult to make a lot of the arguments you want to make. So bringing algebra into geometry and reducing these basic questions in plane geometry to algebraic questions, this is a huge step. Okay, so this plane, as you might have heard it called, is the Cartesian plane. Okay, so it is called the Cartesian plane. Sometimes you will hear it called the Euclidean plane. Those are used fairly interchangeably. So even when you are using the Cartesian plane in terms of coordinates, the Euclidean plane, right, might be used to denote just kind of an ideal plane, not necessarily one that has coordinates on it. But of course, now that you know you can do this, right, you can use these interchangeably. Okay, but this Cartesian plane is of course named after Descartes. And why is this such a big deal? So for instance, a line, right? How can I express a line using this fact? Well, a line L is the set of all points xy satisfying some equation that we call a linear equation, but it's ax plus by plus c is equal to 0. Right. So every single line that you can think of lying in the plane can be represented by an equation of this form. Okay. So note this even takes care of these degenerate lines like vertical lines and horizontal lines, right? Those are also taken care of here. If you want a vertical line, you just pick b equals 0, right? If you want a horizontal line, you pick a equals 0. Okay. All right. If you want a line that passes through the origin, you just pick c is equal to 0. Right? And so this is my linear equation, and now this equation becomes the object of study in a way, right? So I might draw in a line here, right? So I might draw in a line, and so in some geometric computation I'm doing, the line as I've drawn it here is the object of study, but that line gets replaced with this expression. Why is that a big deal? Because doing some kind of operation on a line is hard. It's more complicated if I'm always referring to the picture. But once I have an equation here, it's something that's much easier to get your hands on, right? Now keep in mind, even something as simple as this is something that the ancient Greeks, right, even Archimedes, right, did not have access to this. Okay. So this appendix in geometry is what gave rise to analytic geometry. So Descartes is the discoverer of analytic geometry. He's really like the father of analytic geometry. Fermat did a lot of work here too, as we'll see. So I'll get to him in a bit. So they, in a way, they can kind of be both given credit, but Descartes is really the main discoverer of analytic geometry. Okay. So another example, right? If I have some conic section, right? Well, remember, there's a lot of different conic sections. They can be kind of complicated to think about, right? So you don't only just have like points and lines, but you also have circles, and you have ellipses, and you have hyperbolas, right? Well, regardless of what kind of maybe more complicated conic you have, a conic section can be described as just the set of all points satisfying the equation ax squared plus bxy plus cy squared plus dx plus ey plus f is equal to 0. So let's say I want a circle, right? How do I get a circle out of this? Well, if I take b equals 0 and d and e equals 0 and f equal to, say, minus 4 and a and c are the same, right? We'll make both of them 1. Then this would become the equation x squared plus y squared is equal to 4, right? Which is the circle of radius 2 centered at the origin. Okay. And you can get, those aren't the only circles you can get in this way, so that was just one way of getting a circle here, right? What if I wanted a parabola, right? Well, if I want a parabola, I could, what if I made b, c, and d equal to 0, and e equal to 1, and f equal to 0, we'll say, and a equal to minus 1. Well, then this would be the parabola y is equal to x squared, right? Your favorite simple parabola. Okay, but of course, several other types of parabolas can be obtained by zeroing out or letting these things be equal to different quantities. Okay, and so every conic section could be described as this algebraic thing. This is a much, much nicer way of dealing with these things. So this is bringing algebra into geometry, or reducing geometric problems to algebra. Okay, so this reduces many geometric problems to algebra. What are some problems that you can reduce to algebra in this way? Well, your favorite classical Greek problems: doubling the cube, squaring the circle, trisecting the angle. So, in addition to other types of problems, but these classical problems that we've talked about several times now, those can now be viewed entirely algebraically. And we saw how that works. We were cheating a little bit by using some of our, future knowledge applied to these ancient Greek problems, but this is exactly what it took. So Descartes did not provide solutions to these, and of course we know that these can't be done. So when I say that provide solution, I mean proving that you can't do this with compass and straight edge. Descartes wasn't able to to finish the job. This wouldn't be finished for another couple hundred years, but it is a necessary step. You can't get to the finish line without this intermediate step. Okay. This appendix also included Descartes' law of signs. So if you were never taught this or you don't remember how this goes, here is the idea. So the law of signs says, let's say that I want to find the positive real roots of a polynomial. So say I want to find positive real x such that f of x is equal to 0, where f is a polynomial. Okay. So I'm looking for roots to some polynomial. What is the law of signs? Okay, well, this number, the number of such roots, is equal to v minus 2k, where v is the number of sign changes. So the number of sign changes of f, and k is some positive integer. So 1, 2, 3, 4, so on. Okay. So what's an explanation for this law of signs? So let's say that we have the following type of equation. So due to Tartaglia and Cardano, right, and Ferrari, we now have solutions to cubic and quartic equations, right? It's very complicated, but those have been taken care of. All right, now cheating a little bit and knowing that there's this result that quintics, that is degree 5 polynomials and higher, can't be solved by radicals in that same way. The question becomes, what do I do? There's no general process like that, so what do I do? So Descartes' law of signs actually gives you some hint as to some of the types of tricks that you can use to answer some of these questions. Maybe not exactly find some of these roots, but to answer questions about them. So let's pick a 6th degree polynomial for this case. All right, so for example, let's say we have the polynomial that is x to the 6th minus 3x to the 5th minus x to the 4th plus 2x minus 5, and it's equal to 0. Right, so this is the equation we're solving, or we're trying to find positive real roots of. Now, I have some questions here. So first of all, notice that I have omitted any of the coefficients that are 0. So there is no x cubed term, so I didn't write plus 0 x cubed. Okay, and the reason we're going to do that is because this sign change has to be from, we're writing them in descending order, right? So x to the 6th, x to the 5th, x to the 4th. There is no x cubed, but I omit it. So it's 0x cubed, that gets tossed out. 0x squared, that we don't write that down. 2x minus 5. Okay, and what I do is I count the number of sign changes from left to right. Okay, so I begin with positive. So one sign change to negative stays negative. Sign changes to positive. Sign changes again to negative. So that's 3 sign changes. Okay, so v is equal to 3 here, right? So the number of positive real roots is v minus 2k, so that's 3 minus 2k. All right, so the idea is, what are the possibilities? k can be any natural number. So if k is 1, then this is 1, right? If k is 0, this is 3, right? So the possibilities are 3 or 1. If k is 2, then this would be 3 minus 4. The number would be negative, and it wouldn't make any sense, so we don't continue there. So the possibilities are 3 or 1. That is, this thing either has 3 or 1 positive real roots. Okay. Okay. So, how would we maybe get a better answer than this? How would we be a little bit more thorough? Okay. So, maybe I'll ask that. How would I get a better idea of how many roots? Here's a trick. Let x be equal to minus y. If I let x be equal to minus y, what does this equation become? I would have minus y to the 6 because it's raising it to an even power. That's just y to the 6. So this equation becomes y to the 6. For the odd powers, I'm going to get a negative sign where I had, or I'm going to get another minus sign here. So this is going to be plus 3y to the 5th. It's not going to change the even signs. This is going to be minus y to the 4th minus 2y minus 5 is equal to 0. Let's use Descartes' rule of signs again. In that case, how many sign changes do I have? I start out positive, I change to negative, and then I remain negative the rest of the way. So it actually only has one sign change. And so possibility 1 positive real root. But if this equation, which is the equation I obtained from this first one by letting x be negative y, has 1 positive real root, how many real roots does this one up top have? Well, since x is negative y, this equation has 1 positive real root. This is going to have 1 negative real root. Okay. So no, this did not find that root, but it did tell you at least something about it, right? And this is a degree 6 equation, so this is something that can be really, really nasty. Okay, so being able to do this just with this quick little algebraic trick of we basically did almost nothing, right? Counting sign change in a polynomial like this, once you've got it set up, is pretty easy. So with very little computation needed, we were able to do this. Now, I believe that Descartes stated this without proof. So Descartes stated this without proof. I'm not sure when the first full proof of this fact came about, but Descartes stated this without proof. But he stated the general case of it, so not just special cases. He stated the general case of it, he just didn't prove it. Okay. And so the main contribution of Descartes is analytic geometry, and its importance can't really be overstated. It's extremely, extremely important. So he also published, later on he published some work. So he published the Meditations. He also published Principia Philosophica. So this was in 1641 and 1644 respectively. The last one was basically if you have had a philosophy course and Descartes came up, most of probably what you know about Descartes' philosophy was from that work. It includes his supposedly geometrical proof of the existence of God, which is a circular proof on its face. It's circular reasoning, and people have long wondered. Even his contemporaries thought it was really, really bad arguing, and people have wondered if he was intentionally making this argument so no one could ever. In those days, it was a big deal if someone were to claim that you secretly held atheistic beliefs or anything like that. So people have long wondered whether or not he intentionally made this argument and made it poorly and didn't care that it was a bad argument, considering how well reasoned most of his other writings were. It just seemed very odd and kind of out of character. But I will say that to throw a wrench into that, earlier on in his life, the first book he ever published was called The World, and it was a pro-Copernican book. So it put forth the Copernican model of the universe or the solar system. And just as he was about to publish it, came the Inquisition's trial against Galileo, and basically once it was kind of decreed by the Inquisition that the heliocentric or the geocentric model was the good one, and the heliocentric model was to be shunned. It was bad. Descartes wrote to Mersenne saying that he, I have the quote right here. So Descartes wrote to Mersenne saying that this has so strongly affected me that I have almost resolved to burn all my manuscript, or at least show it to no one, but on no account will I publish anything that contains a word that might displease the church. So whether this was due to him just being really, really devout, or whether he was really, really cautious of running afoul of the Catholic Church is not really clear. But at least as early as that, it shows that he was really, really aware that it was very easy in those days to write some seemingly innocuous scientific thing and get massively punished for it. So anyway, he seemed to be not willing to err on the side of philosophy that would get him punished. Anyway, the next name is the greatest amateur mathematician of all time. So Fermat, the greatest amateur mathematician. Amateur not in his level of skill, just because being a mathematician was not his job. So the greatest amateur mathematician of all time. You'll see by the time I'm through talking about him why this is an apt title for him. So he was a counselor for Parliament. So he only did math in his spare time. He did devote quite a bit of his spare time, and basically all of his spare time was devoted to math, but he only did math in his spare time. And he basically he's a little weird because most of his math was done just in his spare time. He never published a single book. So he never published any book, any work like that, because again, he wasn't a mathematician. He was just doing it for fun mostly. So he never published a single book, article, work, whatever. All right. In fact, you might say, well, how do we even know what he did, right? If he didn't publish any book, any work, or anything like that, how do we know what he did? So you might recall the first guy mentioned in this block of mathematicians was Mersenne. So he did correspond frequently with other mathematicians. So namely Mersenne. And it's through this correspondence that we know most of what he worked on. There's one particularly funny example that's very famous now on account of the situation. So that'll be the last thing I talk about with Fermat. But he, so what did he do? He basically did work in analytic geometry, very similar to Descartes. He also did work in analytic geometry. Enough so, so similar to Descartes, enough so that he could be considered like a co-discoverer of analytic geometry. So he really did. He was doing this work at about the same time Descartes was, and so they can definitely be. It would be fair to say they're co-discoverers of analytic geometry, even if Fermat doesn't necessarily always get credit for those particular contributions. So he studied using this analytic geometry. He studied tangents to curves. Maxima and minima. Okay. And areas under curves. So he came very close to discovering calculus. Okay. So he was really, really close to the path of discovering calculus. Soon we are going to get to a mathematician in the next block of mathematicians I talk about that is kind of the first, when it came to the problem of finding areas under curves, he's the first mathematician to surpass Archimedes. And he's also the first person to compute an integral. So that's coming next. That's not Fermat. Fermat came close, but he was just out of reach of those things. This is Cavalieri I'm talking about. Okay, so what else did Fermat do? Fermat is best known for number theory contributions. In fact, except for a couple of exceptions, like Thabit Ibn Qurra and his 3-2-1 numbers, right? The Thabit numbers, like was a topic on your exam. Apart from some exceptions like that, Fermat's work is the first big push into number theory since Diophantus. And ironically, one of the most famous things Fermat ever wrote was in the margin of a translation of Diophantus's big work. Okay. And so, what are some of his number theory contributions? So, first, Diophantus knew that a prime number of the form 4n minus 1 is never the sum of two squares. Right? So Diophantus knew that a prime number of the form. So a number like this is not always prime, but when it is, prime number of the form 4n minus 1 is never the sum of two squares. Fermat, being inspired directly from Diophantus, he was reading Diophantus. So Fermat showed that a prime of the form 4n plus 1 can be written as the sum of two squares in exactly one way. Okay. So Fermat proved this. Fermat also proved, here, maybe I'll underline that. So Fermat also proved that every odd prime p can be written as the difference of two squares in one and only one way. So any odd prime p can be written as a sum, or sorry, a difference, not a sum. Can be written as a difference of two squares in one and only one way. So there's exactly one way to write this. So any odd prime p can be written as a difference of two squares in one and only one way. So how is this proven? Well, basically, so proof of 2. There is the obvious way to write it. So I can write p as this kind of trivial square. So 1/2 p plus 1 squared minus 1/2 p minus 1 squared. So if you work this out, this will indeed do the job. So 1/2, and why does this do the job if p is odd? Well, 1/2 p plus 1 and 1/2 p minus 1 are integers since p is odd. You might say that's kind of a weird way of saying it. P odd, isn't that all primes? Well, it's all primes but 2, right? So this is just a funny way of saying this is true for every prime except 2. Okay. So since p is odd, these are both integers. So here's one way of doing it. Now I have to show that this is the only way. How do I do that? So to show that this is the only way that this could work, suppose that it's written in another way, right? So suppose that I have x squared minus y squared, and this is equal to p. Well, I know how to factor this difference of squares now, right? So this is x plus y, x minus y. Just my difference of squares factorization. But this is, if x and y are integers, then this is integer times integer, and this is equal to p. But p is prime. So I have this expression, p is equal to an integer times an integer. Since p is prime, what do these integers have to be? Well, they have to be 1 and p. Well, which one is 1 and which one is p? The bigger one is p, and the smaller one is 1. And so, x plus y is equal to p, and x minus y is equal to 1. Right? But then if I solve here for x and y, what do I get? If I solve for x, I get exactly 1/2 p plus 1. And y is 1/2 p minus 1. Hey, that's exactly these two. All right, so this is the only way of doing it. Okay. All right. What else was Fermat known for? Something that he has named after him. If you take a course in number theory, one thing that you will learn right after you start doing modular arithmetic stuff is what's called Fermat's little theorem. It's called the little theorem to distinguish it from the big named Fermat's theorem. So what is Fermat's little theorem? This says that if p is prime and a is an integer that is not a multiple of p, then a to the p minus 1 is a multiple of p. Okay. Rather than prove this, which requires the binomial theorem, so proof uses binomial theorem. So I'm going to omit that for a second, but and I might prove it in a later lecture. But for now, let's just look at some examples of this. So let's take like let's take I don't know. Let's take a prime, maybe 7. All right, so 7. So let p equal 7. And let me pick an integer a that is not a multiple of p, so a is equal to 2. Right? Then this should say that 2 to the 7 minus 1 is a multiple of 7. Well, what is this? This is 2 to the 6 minus 1. 2 to the 6 is what? 64. So this is 64 minus 1, so this is 63, which is a multiple of 7. Right? 7 times 9. Okay, and this will work for any such numbers like that. Okay. All right, so that's a neat fact. Now, the most famous named thing after Fermat is Fermat's last theorem. FLT. Okay. So, first of all, what's the context here? So it has a really funny historical story. So Fermat is reading a translation of Diophantus. Okay, and of course, as a treatment of that, Fermat comes across the equation x squared plus y squared is equal to z squared. Okay, and in Diophantus's work, this is given a solution. And Fermat thinks for a second, and he's like, well, okay, so this is the Pythagorean equation, right? So how many integer solutions exist, right? So how many solutions x, y, z with x greater than 0, y greater than 0, z greater than 0, and x, y, z integers, so they're positive integers, exist? Well, you already know the answer to this. There's infinitely many Pythagorean triples. These are just Pythagorean triples. So the answer is infinitely many. Okay. So Fermat thinks for a second, and he says, okay, well, what about if I rewrite this equation, but instead of using x squared, y squared, and z squared, I use x cubed, y cubed, and z cubed? So the question is, how many non-trivial solutions exist. When we say non-trivial, we mean that x, y, and z are all positive and they're all integers, right? So you can't use like the cubed root of 5 or something here. Okay. So how many non-trivial solutions to this thing exists? And Fermat thought about it for a while, and he's like, I think I can show that none of them. There's none of these, right? So the answer is none. Okay. And then Fermat thought, what about x to the fourth plus y to the fourth is equal to z to the fourth? How many non-trivial solutions? So question, same. How many non-trivial solutions? And the answer, according to Fermat, is none. And so Fermat writes x to the n plus y to the n is equal to z to the n, where n is greater than 2, so n's at least 3. Okay, so question, how many non-trivial solutions? The answer is none, according to Fermat. This is called Fermat's last theorem. So this is FLT. This is Fermat's last theorem. The assertion that there's none of these non-trivial solutions to this equation, x to the n plus y to the n is equal to z to the n, where n is bigger than 2. This is Fermat's last theorem. And what is so funny about it is he stated this in the margin of a work of Diophantus. Okay, so he was reading Diophantus and he was scribbling this in the margin of his translation. Okay, so he scribbles this and he says there's no solutions. And then he says, and this is the funny part, I have a proof. I think he even says like a wondrous and marvelous proof, a miraculous proof of this fact that the margin is too small to contain, right? So he's like, I know exactly how to prove this, but I can't write it here because the margin's too small, right? But trust me, right? I know the proof of this. And of course, no further work of Fermat was found on this. And it's very unlikely that he had a correct proof of this fact because this fact would take until 1994 to be worked out. Okay, so this was proven. This is true, that there are no non-trivial solutions to this thing. Okay, this is known as Fermat's last theorem, and this was proven, proven by Andrew Wiles in 1994. Very recent. And the proof of this took mathematics through some areas that wouldn't at a first glimpse seem like it had anything to do with a question like this. So this did a lot for a field called algebraic geometry. So I'll talk a little bit more about that next time, and then we will finish up with 17th century French mathematicians and go toward the next block of mathematicians, which will end with Leibniz. He will be kind of the last one we consider in the next block. All right. So anyway, I will see you all on Friday.